What's up, YouTube? It's your boy, Professor J, coming at you. I got one thing to talk about, and that's engineering economics. I got an example for you. Let's go! Hey, where'd I go? Okay, IU Health wants to buy a diagnostic machine to detect certain types of heart defects, and they have an option of two vendors to buy from. BR Medical offers a machine costing $300,000 with a salvage value of $18,000 after a useful life of 7 years. Variable operating expenses related to clinical labor and direct materials are estimated to be 8% less than the machine they currently use, which costs approximately $250 per procedure. Materials cost for the BR Medical machine are 40% of the total variable costs. A new company, Indiana Medical Solutions, or IMS, sells a similar machine. The price is $600,000, but it has an innovative system to reduce waste. As a result, the material costs for each procedure are cut in half relative to the BR Medical machine. The salvage value of IMS's machine is $36,000 after a useful life of 8 years. The expected price charged to patients is $265 per procedure, no matter which machine is used. They plan to conduct, on average, 250 procedures per month. First, we're asked to fill in the following table, which summarizes all of the information that we're going to need in order to do our economic analysis. Pause the video, take a few minutes to try and fill this in yourself, and then we'll talk through it. Okay, so let's start with the easy items. We have some things that were given in the problem that don't require any calculation. That includes our initial investment, our salvage value, and the useful lifetime. So we can just fill those in right off the bat without having to do any sort of conversion at all. However, our expenses and revenues are a little bit more complicated. We're told that the revenue is actually going to be the same no matter which device they use. So let's do that one first. What we're told is that we're going to charge $265 per procedure and that we're going to do 250 procedures per month on average. Since there's 12 months per year, this gives us the expression that we need to calculate our revenues, and it's the same for both devices. The annual expenses, however, are going to be different. What we're told is that our current expense per procedure is $250, and that the BR Medical device is going to be able to reduce that by 8%. So what we're going to be left with is a cost per procedure of $250 times 92%, which is $230. And then we've got 250 procedures per month and 12 months per year. So that's going to give us our expenses for the BR Medical device. On the IMS device, what we know is that material costs are 40% of the expenditures per procedure, and that they claim we can reduce that material cost by half. And so we've got an expression like this where $230 is our base cost, 60% of that is labor and other costs, and that's unchanged. But then we've got $230 times 40%, which represents our materials cost, and we can cut that in half. So we'll take half of it, and then we take all of that and multiply it by our 250 procedures per month times 12 months per year. And that's going to give us our annual expenses for the IMS device. That's all we need to know in the table to begin our benefit cost analysis. The next question that we need to answer is, what's the benefit cost ratio associated with each project, assuming a hurdle rate or MARR of 10%. To do a benefit cost analysis and compare projects, first we need to verify that both of the projects are acceptable in their own right, so we need to calculate the benefit cost ratio for each one separately and verify that it's greater than 1. If we look at Excel, you can see that we've got everything laid out the same as in the problem statement, and I've also added our conversion factors for P given A and P given F, where N is equal to the useful lifetime for each of the devices. Now, if we use the conventional benefit cost ratio formula, we just need to calculate the present worth of our expenses, our revenue, our salvage value, and so on, and then form that into the numerator and the denominator. To get the present worth of our expenses, we're just going to take the expenses value on an annual basis and multiply it by P given A, and the same is true for the revenue. For the salvage value, we can take its present worth by multiplying it by P given F. And that gives us our present value of benefits and costs, where the benefits are just the present worth of the revenue, and the costs are the initial investment minus the present worth of the salvage value plus the present worth of our annual expenses. Then the benefit cost ratio of each device can be found by just taking the ratio between the present worth of the benefits and the present worth of the costs. We can see that they're both greater than 1, so both devices would be justified in using on their own. Now we need to figure out which one is preferred. We're asked to consider which machine we would recommend purchasing under two different sets of conditions. In the first case, we assume a planning horizon of 5 years, that the machine's purchases are non-repeatable, and that means we need to figure out what the market value of the machines are at the end of the 5-year planning horizon. To do that, we're going to use straight line depreciation. In the second situation, we're asked to use a planning horizon of 8 years, and to evaluate whether or not we would recommend purchasing the same machine as if we had the 5-year planning horizon. In this particular case, now we have one of the machines that has a useful lifetime of only 7 years, and so the non-repeatability assumption is going to come into play. We need to figure out what the future worth of the 7-year machine would be after 8 years, assuming that any net profits of the project would be reinvested at the hurdle rate. For the first question, I want to show you how to do it using an incremental benefit cost analysis. At first glance, this seems like it would cause problems because we have the same revenue in both cases. So if we take the incremental benefits, it seems like there are no incremental benefits if we're using a conventional benefit cost ratio, right? Well, the way that we solve this dilemma is to go back to our principles for good decision making and realize that we need to just focus on the differences. If we're doing an incremental analysis, that's exactly what that means. You're focusing on the increment or the difference between the two projects. And since there is no difference in revenue, we're going to reframe this as a cost alternative to say which device allows us at least cost to perform these medical procedures. If that's the case, then our initial investment in the BR Medical device is smaller, so that's what we're going to use as a baseline. And we're going to think of the initial investment in the IMS device as being the incremental cost in order to achieve savings in the future through smaller expenses. So that reduction in expenses is what we're going to frame as the benefit. If we do that, we can look at our 5-year planning horizon, recalculate our P given A and P given F factors, and then follow the same procedure as we did before. We need to calculate the present worth of our expenses and the present worth of our benefits, where now the benefits are the reduced annual expenses associated with the IMS device. So to do that, we're told that we need to use straight line depreciation in order to get the market value of each device at the end of the planning horizon. So in this case, we have our formula. Remember, for straight line depreciation, we're taking the same deduction in every year, and so the book value is just the initial cost basis, or the initial investment, minus the deduction, which is the difference between the initial investment and the salvage value divided by the useful lifetime, and then we just multiply by how many years we want to go. So in this case, that would mean that we're taking 5/7 of the difference between the $300,000 initial investment and the $18,000 salvage value for the BR Medical device. And for the IMS device, we're taking the initial investment of $600,000, subtracting the salvage value of $36,000, and multiplying it by 5/8. Then we multiply that book value at the end of the planning horizon by our P given F factor in order to get it to present worth. We said that the benefits are going to be the reduction in annual expenses that we can achieve by using the IMS device. To calculate that and put it in present worth terms, we're going to take the annual expenses for each device, multiply it by a P given A factor, and then take the difference. On the cost side, the difference in cost that we need to calculate is the difference between the capital recovery amount expressed in present worth terms. So we want to take the initial investment minus the present worth of the market value at the end of the planning horizon. So there, we just have our initial investment and subtract off the present worth of the book value in the 5th year that we calculated previously. Once we've done that, we can calculate the delta in benefits and the delta in costs, where the benefits are the difference between our present worth of annual expenses. The delta costs are the difference between that capital recovery amount expressed in present worth terms. And then we can take the ratio of those, see that the benefit cost ratio of the incremental difference between projects is greater than 1, which implies that the IMS device is our preferred alternative. Next, we're asked whether or not we would choose the same device if we use an 8-year planning horizon instead of 5. The difference here is that now the planning horizon is longer than the useful lifetime of one of our devices. If that's the case, remember that what we do is calculate the future worth of the net profit associated with the project at the end of its useful lifetime, and then we make the assumption that that net profit is reinvested and has a return equal to the hurdle rate for whatever remaining time is between the end of the useful life and the end of the planning horizon. In this case, the IMS device has an 8-year planning horizon and an 8-year useful lifetime, and so the future worth of the initial investment, the expenses, the revenue are all the same at the end of the life as they are at the end of the planning horizon. So you can see the net present worth we can calculate really easily. For the BR Medical device, we can calculate using a 7-year useful lifetime what the future worth is of the initial investment, the annual expenses, and the annual revenue. And that gives us a net present worth at the end of t equals 7. Then we project that forward to t equals 8 using 1 plus I to the n for 1 year, where I equals the hurdle rate. And since we have a 10% hurdle rate, that means we have an increase of about $43,000 over the net present worth at t equals 7. You can see that at the end of the planning horizon, the IMS device is still much greater in terms of net present worth value, even though we have an additional year of reinvestment from the BR Medical's profits. So yes, we would make the same decision again. I'll post the problem and the spreadsheet for this example on Blackboard and the Google Drive so that you can refer to it, look at the formulas, and play around with it yourself. That's all for this episode. If you enjoyed this video, I need you to share, like, and subscribe. So smash that like button, ring that bell, and we'll see you next time. All right.